Dear students, welcome to Build from Basics YouTube channel. Active and reactive power, together they make the apparent power. The active power is the multiplication of RMS voltage V and RMS current and the cosine of angle between them. The units of active power is watts or kilowatt or megawatt. The reactive power is the multiplication of RMS voltage, current and the sine of angle between voltage and current. The unit of reactive power is kilovolt ampere reactive. kVAR or volt ampere reactive or megawatt. It depends on the amount of reactive power. And finally, the apparent power S is the units of apparent power is either volt ampere or kilovolt ampere or megawatt ampere. This is just reminding some basics to you before we go to the pure resistor. Now let's talk about the relationship between voltage, current and power in a pure resistive circuit. So the circuit shows AC source is supplying a resistive load. The transformer represents transmission system. The figure shows here the instantaneous voltage, current and power waveforms across resistor. The blue waveforms here, see the blue waveform in the right side is the voltage and red one is current. As you can see, the current in the resistor, it is in phase with the voltage. The angle between voltage and current is 0. So the green waveform is the instantaneous power across the resistor. It is the product of voltage and current. The instantaneous power is measured in volt amperes. The power is always positive, both in positive and negative half cycle of the voltage. Okay. Now, if you want to see the average of this active power, so this purple line, straight line is the average of active power. So it is the it is shown in purple dash line. You see it's exactly positive and it's the middle of this green curve. The pure resistor only consumes active power. The active power is multiplication of voltage, RMS voltage, current and cosine of angle between them. And pure resistor doesn't consume any reactive power because pi is 0, Vi sin pi is 0. That's why it doesn't consume any reactive power. Q is 0. And finally, apparent power is equivalent to active power only. Okay. So now let's investigate current, voltage and power in a pure inductive circuit. The circuit shows AC source is supplying an inductive load. The instantaneous voltage, current and power waveforms across the pure inductors. Pure inductor is shown, the figure beside. Here the blue curve and red curve are the voltage and current in the circuit. As you can see, the current here lags the voltage because this is the voltage waveform, this is the current. Current lags the voltage by 90 degrees because it's a pure inductor. It lags the voltage by 90 degrees. So the reason I will explain here, okay, why it lags by 90 degrees or why basically current lags by voltage in a pure inductor. So basically you know that when a time varying voltage applied across a pure inductor, an opposing voltage called back EMF is produced by the inductor due to its self-inductance. It's also called Lenz's law. This back EMF opposes and limits the current flowing in the inductor. So it opposes the current flowing in the inductor. Therefore, current through the inductor cannot follow the voltage across it and it always lags behind it. Therefore, if the inductor is pure, the current lags behind the voltage by 90 degrees. So because of this back EMF and self-inductance, the current cannot follow the voltage and it lags behind the voltage by 90 degrees. Now, let's look at the instantaneous power in the inductor. The green waveform is instantaneous power here. It is a product of voltage and current. The instantaneous power is measured in volt ampere. As you can see, the instantaneous power pulsates between the identical negative and positive half cycles, negative cycle and positive half cycles, with double the frequency of supply voltage. So this is supply voltage frequency. It has only one complete cycle, but the power waveform has 2 cycles. That's why the frequency is double the frequency. But if you see the average of this green curve, that is the power, is 0 because it has equal negative half cycles and equal magnitude of positive half cycle. Basically, then the average power is nothing but the active power across a pure inductor is 0. So the average instantaneous power is called active power and it's 0, and it is shown as a dashed line in this figure. Now, the active power in an inductor, it's a multiplication of VI cos pi. V here is RMS voltage and I is RMS current, and cos pi. So pi is the angle between instantaneous voltage and current. It is 90 degrees. That's why by equation also active power is 0 and the reactive power is VI sine pi. Sine pi is 1 and therefore VI sine pi is equivalent to V multiplied by I. That means the apparent power constitutes only reactive power in a pure inductive circuit. There is no active power. That's why S is equivalent to Q. Now let's talk about relation between voltage, current and power in a pure capacitive circuit. Here the circuit source, AC source, is supplying a capacitive load. The instantaneous voltage, current and power waveforms are given in this figure, right? The blue waveform is voltage waveform and red is current waveform. As you can see, the current waveform is leading the voltage waveform. That means if the voltage is 0, the current is already at maximum. When the voltage is, so that means the current waveform is leading the voltage waveform by 90 degrees. That means in a pure inductor, current leads the voltage by 90 degrees. The reason is, the capacitor is nothing but what? It's 2 conductors separated by a dielectric medium. So when a capacitor is connected across a voltage source, immediately the voltage doesn't build up instantaneously. So the capacitor starts charging slowly by taking the current from the source. Therefore, in a purely capacitive circuit, the voltage cannot increase in phase with the current, as capacitor needs some time to charge. This makes the voltage to follow the current, and the voltage reaches its peak value sometime after the current reaches. The result is that in a pure capacitive circuit, the current always leads the voltage by 90 degrees. If the capacitor is not pure, then the angle is little lesser. But in a pure circuit, it is 90. Pure capacitive circuit, the angle is always 90 degrees. Now, let's look at the instantaneous power. Similar to the inductor, in the capacitor also, the instantaneous power pulsates between positive and negative half cycles, and the frequency of this power is double the frequency of voltage. So as the voltage has 1 cycle here, it is a blue curve, and the power has 2 cycles. So but if you see the average value of this power, it is nothing but 0. The purple line is average value because it has both positive and negative half cycles. The average value of power in a pure capacitive circuit is 0. Basically, there is no difference between inductor or capacitor in terms of instantaneous power. Only the difference is the sign. So during the first 90 degrees, in an inductor the power is negative, but in a capacitor it is opposite, positive. So it starts from, in an inductor it starts from negative to positive. In a capacitor it starts from positive to negative. That's all. That is only the difference. So if you look at the equations for active and reactive power, basically the angle between voltage and current is minus 90 degrees. That's why even though if it is minus 90, cos minus 90 is 0 anyway. So active power is P is equal to VI cos pi, that is 0 watts. And reactive power is minus VI, because sine minus 90 is minus 1. And finally the apparent power is equivalent to reactive power. So it is similar to inductive circuit. So now this is the combined waveforms of voltage, current and power of a resistor, inductor and capacitor. This is presented here for a comparison. In reality, a pure resistor, capacitor or inductor never exists. The resistor is associated with some inductance and capacitance, and inductor always has some internal resistance, even also some parasitic capacitance across the inductor. Even capacitor also has some some resistance across it. So, but on top of that, in power system, loads are always mix of resistive, inductive and capacitive loads. So you can't find any pure resistive resistor or inductor or capacitor in real life. Now let's do some simulations. So far we have discussed theory behind the circuit elements. Now let's do the simulations. What I do, I'll show you a simple simulation to understand these three circuit elements: resistor, inductor and capacitor, and show you that there is always RMS current flow between from the source and the load, irrespective of type of load. That means whether it can be resistor or inductor or capacitor, there is always equal amount of RMS current flowing between the source and the load. So therefore the transformers and generators always have to supply this load irrespective of type of load. So now let's consider a single phase circuit here with the three network elements: a resistor, inductor and capacitor, as shown here. The circuit elements are shown in the table. So what we'll do, let's take a single phase supply, 11 kV supply. 11 kV is a phase line voltage, and the phase voltage is then 6.35 kV. Let's take a transformer of 23 kVA and with a ratio 6.35 kilovolts in the primary and 230 volts in the secondary. So then the rated current in the primary is 3.62 amperes, and the secondary is 100 amperes. To supply, now let's calculate the resistor, inductor and capacitor using these formulas. So Z is impedance here. Z is equal to V square by S. Here V is the voltage, that is 230, and S is the power, 23 kVA. So R is equivalent to Z, and L is Z by 2 pi F, and C equivalent to 1 by 2 pi Fz. If we use these formulas, we will get these values. R is equal to 2.3 ohms, and L inductor is 7.32 millihenry. So that means both resistor, inductor and capacitor, they consume equal amount of power, but resistor consume active power and inductor consume reactive power, 23 kilovolt ampere reactive power, and capacitor produce 23 kilo kVAr reactive power. So the number is same, but the units are different. So now let's see the simulation results. So PSCAD software is used for the simulations. You can see any other software. You can use any other software of your interest, like MATLAB or others. But I have used PSCAD here. So now let's see the simulation results. Here, first let us look at the pure resistive circuit. An ideal AC voltage source and ideal transformer are chosen to focus only on the impact of type of load. So, type of load and the loading on the transformer. Let's run the simulations. So here, on the right side, the blue and red curves in the first graph are the instantaneous voltage and current respectively. As you can notice, both are in phase. The green curve and the green curve below is the instantaneous power. The power is always positive and the average value is around 23 kilowatt. So the graph below shows the RMS voltage and RMS current. As you can notice, the RMS voltage is 230 volts and RMS current is 100 amperes. Now remember this value 100 amperes. So now let's go to the replace with the inductor and run the simulations. So now it is an inductor, run the simulations. The right side, the blue and red curves in the graph are instantaneous voltage and current. As you can notice, the current here lags the voltage by 90 degrees. The green curve in the graph below is instantaneous power. The power equally oscillates between negative and positive half cycles. That's why the average power is 0. The RMS voltage and current shown in the graph below. The RMS current is 100 amperes, which is equivalent to the resistor case. So even resistor is also drawing 100 amperes RMS current. Now let's replace this inductor with a capacitor and see. So now let's run the simulations. Again, the right side graph shows some results. The blue curve is voltage and red curve is current. As you see, the current leads the voltage by 90 degrees. And the green curve below is power, instantaneous power. It oscillates between positive and negative half cycles. So you can also see that the frequency is double the frequency and the average value of power is 0. And the current, RMS current is 100 amperes, which is equivalent to the inductive and resistor case. Okay. Now the simulation results combined or consolidated results are given in this slide. So the as you see, the simulation results of instantaneous and RMS values of voltage and current and the instantaneous power of a pure resistor, inductor and capacitor are presented here for comparison. From these results, it is clear that all the components draw 100 amperes RMS current irrespective of type of load. So all these elements, that is resistor, inductor or capacitor, they equally load the transformer and the AC generator who is supplying the energy to them. Only the resistors perform the real work and consumes energy, and reactor and capacitors, they don't do any work and they don't consume any active power. But reactive power is the reason for the current flow. Because there is current flow, right? So you can see the 100 amperes current flow. Why? Because still the inductor consumes reactive power and capacitor produces reactive power. That's why there is always a 100 amperes current is involved. Therefore, it is a must for the transformer and AC generators to supply this current to the loads. So if you are supplying some current to the load, even though the inductor and capacitors are not consuming any energy and not doing any real work, still the transformer and generator has to supply. That's why it is very important to rate the transformer and AC generator in kVA or MVA or VA, because the current through the transformer winding depends on the load current, right? So it doesn't know whether it's a resistor or inductor or capacitor. Basically, what is drawing that current? Basically, it doesn't know. So that's why it is very important to provide the rating in kVA or MVA. Now that's all for today's, and as you see, the here I have shown you the active power, basically average active power. In the resistor it is 23, and inductor and capacitor is 0. But anyway, so that's all for today's presentation, and thank you very much for watching this video. We hope it is helpful to you. We request you to subscribe Build from Basics YouTube channel by clicking the bell button, and share with others for those whom you think it is relevant. This will encourage us to post more such videos in future. You can always post your questions in the comments, and your reviews why transformer and alternators are rated in kVA. So you can also post your reviews why it is rated in kVA, and let us know the topics, and also let us know the topics that you would like to know more details, that you would like us to make videos in future. And thank you very much, and all the best.